In this video, we are going to talk to Kenneth Wood. And now you may be like, who is Kenneth Wood? He is the creator of Saturn PCB Toolkit. This is a very popular free software for hardware design engineers. And I have been using Saturn PCB Toolkit for years. Very often I use it, for example, if I need to double check what is the maximum current, what can flow through a via or through a track. And very often I use this calculator if I need to double check impedance of tracks in my PCB. And because this calculator is free, I wanted to know a little bit more about the calculator. I wanted to know, for example, what is behind these equations, because I wanted to understand how it was created, if, for example, if I can trust these calculations. So I sent an email to Ken, and I asked him if we could make a recorded call where we would talk about this calculator. And I found it super interesting because Ken explained some of the parameters in the calculator which I had no idea how they can be used. For example, he explained some of the equations which are behind some of the calculations, and he even showed me some of the calculators which I had no idea about. For example, did you know that in this calculator there is also possible to calculate impedance of vias in differential pairs? I had no idea there is this kind of calculator. So I really hope you will find this video useful. Basically, in this video, I'm going to play this call, which I recorded with Ken. We are going to talk about this calculator, and we are going to start with conductor properties. So when I start playing this call, Ken will open the Saturn PCB design software. He will basically open the the conductor properties calculator. It is this one, which is here. And he will start explaining basically how this calculator works. And I really hope you will find it useful. Here it is. Here is my recorded call with Ken.
What this is saying, a 5 mil conductor with an ambient temperature 23 degrees. It's 23 degrees Celsius in your room, wherever. The amount of current that it takes to raise that conductor 1 degree Celsius above ambient is 0.2653 amps. That's what that means. It does not mean that the 5 mil conductor can only handle 0.26 and that it'll burn up at 0.26. It just means that that's the current flowing through the conductor that will raise the temperature of that trace by the specific temp rise that you call out. If I go up to 20, it goes up to 0.99. Most people, in my opinion, you wouldn't want to get anywhere near 60. You can, but especially with these materials now are so high temperature compared to what they used to be. But 1.58 amps will raise at 60 degrees, a 5 mil trace. And based on these inputs. And I have this set up right now with all of the modifiers turned on in the 2152, meaning if you add a plane to it. your amperage goes up because the plane is helping to dissipate a lot of that heat. This is something that I know for a fact. I've done boards thinking that I'm going to add all this copper to dissipate heat, and it dissipated so much heat I could barely solder the parts on. And I actually had part failures. I had to start pulling copper back from the internal layers because parts just weren't soldering properly.
Really?
A lot of the QFNs, well, the IPC calls them BTCs now, bottom terminated components. I had a lot of failures. So I had to start pulling copper back and pulling copper out from some of the internal layers underneath those BTCs because they just weren't soldering properly. And keep in mind, this was multiple people soldering them. These are high-end vendors. There's not it's not Joe Blow's assembly shack. They had real issues with quality until I started pulling some of that copper away. So adding a plane definitely pulls a lot of heat away from your trace. There's a parallel conductors in here. You can add parallel conductors, and it basically takes your amperage and divides it by 16 or whatever you've got in there. There's more about this in the IPC 2152. I tell everybody that if they don't understand how this works, you've got to get the IPC 2152 because it's radically different from the 2221, where the 2221, if we go to here, none of the multipliers are valid for that. And back in the 1940s, when they created the formula, I think it was the 40s. It was a long time, 40s or 50s. It was assumed that an internal trace couldn't handle as much current as an external trace. So they came up with a formula for an external trace that today is surprisingly accurate, which is still in use today in my toolkit and many others. And they just derated the internal trace by 50%. That's all it was. That's all they did. And the IPC 2152, I believe, I could be wrong about this, but I believe it was Lockheed Martin that did most of the work for the 2152. Could be Northrop Grumman. I apologize to either one of them if it's not, but I thought it was Lockheed Martin. Because if you look through the IPC 2152, there's no formulas. It's measurements. Somebody took a thermal camera and measured conductors at certain ambience with certain current flowing through them. Well, what they found is that internal traces can actually handle slightly more current than an external trace because the FR4, they actually used a polyimide, 70 mil polyimide, but it could actually handle more current than the external trace because the fiberglass was such a good conductor, a good thermal conductor. So I tell people, if you don't want to use the so bottom line is the 2221 is obsolete. I tell people don't use it. If you want something that will work all the time, use the 2152 without modifiers. That will give you the most conservative values of your trace. That is with the external and the internal formula being exactly the same, which is what they tell you in the 2152. You can use the same model for both internal and external and be done with it. That will give you a conservative value that will always work. The modifiers come in because through their testing, they said, well, okay, now let's add a plane, see what that does. Let's add, let's change the PCB thickness, see what that does. And they came up with a list of multipliers saying, if you add a plane, you can add 20%. And actually, Jack Olson, I don't know if he's still with Caterpillar, but he did a phenomenal amount of work on this, created an Excel file, the how-to something 2152. And he helped me out early on when this came out to explain a lot of this, because I guess he was involved with the final release of the 2152, something like that. He was involved with the people, but he was a fantastic contact to have at the time and explained a lot of this stuff. So bottom line is if you don't need the modifiers, if you're not on the hairy edge, use it without modifiers and you'll never go wrong. If you truly need to carry 10 amps to a 5 mil trace, then by all means put the modifiers in. But just keep in mind they're just guesstimates based off the 2152. I'm not saying they're not accurate. I'm just saying, they're not. It's not some hardcore simulated result.
The frequency, is it important for the current? No, I guess that's for skin depth, for example.
No, it's skin depth. Yeah, it's only for the skin depth.
So this specifies how deep the current will basically flow.
Yeah, correct. As you go up in frequency, the electrons tend to move to the outer shell of the wire, and the same with the conductors. That's a long complicated topic. People are welcome to look at skin depth. I believe Doug Brooks has a white paper on skin depth, and the skin depth percentage that you're not supposed to go below some value. I don't remember exactly what it is, but because if you go too deep, it starts adding resistance, RF resistance or something like that. It's been years. I should apologize. Some of these formulas I put in years ago, and people ask me from time to time, "Hey, what's that?" I'm like, let me look that up, because that was about 10 or so years ago. I coded that in. So, but that's out there for people to look at.
Okay. Next, I see fusing current. I guess that's when the track will be damaged.
That's a really cool thing that's in 8.0. I radically changed this whole thing. Conductor width, time in seconds, and there's also a Onderdonk, however you pronounce that, multiplier. And I put a link to a page from PCD&F, and of course you've got spam in your way.
Skip to content. There is on the top of the page.
Oh, there we go. Skip to content. And there's a good example here that I based this off of, and it says this is what here's a multiplier, and here's how the multiplier works, and you can read all about that. But this, if somebody's really looking for where will my trace actually burn up, this is the tab you want to be looking at, not the conductor properties.
Did you test this one?
I tried to. Copper can handle a surprising amount of current before it burns up. I think a lot of it has to do, like the trace in the picture. What happens is the glass transition temperature is exceeded, and the material just underneath the trace melts or burns away or becomes loose. And as soon as that trace pulls away from the thermal thermal heat sinking of the board itself, then it burns up immediately. But if you can keep the trace on the board, they can handle a surprising amount of current. I tried one. I made a LinkedIn post a few weeks ago, if you saw it, where I took a trace and I tried to burn it up. And my power supply, unfortunately, has a current limit, so it would shut off. So I put a nick in it, and I put a deeper nick, and I put a deeper nick, and I couldn't get the thing to burn up. So no, I have not personally tried this. And they tell you in the article that this isn't extremely accurate, but it's pretty good. Yeah, it's the article that I linked to is it's worth the read. Well, time is also an important variable. So yeah. I mean, if you put it, if you've got it, it's hard to explain, but the time is an important variable that you have to look into. You have to. I've actually got the formula right down here that shows that. And it has the melting temperature of copper, and actually I put this in here because the formula works off the circular mill, not the conductor cross section. So I have to convert the conductor cross section to circular mills, which is some multiplier that I just don't remember off the top of my head.
Okay. Okay, so let's click on the conductor impedance.
Conductor impedance.
Okay. And let's talk about this specific calculator. So what I know what this calculates, but you can explain.
This is a microstrip calculator, the surface microstrip, and I find it to be pretty accurate. I'm modeling it against Cadence Allegro and some others. I know Cadence Allegro. I thought I saw a tech note a long time ago from Cadence because I had asked them a while ago what formulas they use, and they sent me a tech note from Cadence. And I thought that they used the Symbion engine, just like Altium does now. So it's pretty close. I mean, none of these formulas are, these are all combinational logic style formulas. So we're not doing any type of advanced EM simulation here. So they're not always going to be exactly accurate to a full-blown electromagnetic simulator, but I find them to be close enough, very close.
So when someone would like to calculate impedance of a track, for example, then they can use this.
Correct. Yeah, and I've also put frequency in there because frequency does affect the effective dielectric constant, which can affect, put in here, 2450 megahertz. You can see that it's very slight, but it does have some effect at that.
I have actually never really changed this frequency value.
Yeah, it's slight, but I put it in there. So to answer your question, you know, are they accurate? I've personally spent thousands of hours on this thing, going over formulas. Most of them I'm very happy with. There's a few out there that I'm still not 100% sold on, but without an EM simulator engine, it's as close as I'm going to be able to get with these formulas, because some of these formulas are just not accurate with every single geometry out there, which is what I've noticed. The microstrip I find to be pretty accurate. People ask me all the time, sorry, I keep hitting the table there. People ask me about adding the solder mask, and I've tried some formulas. I couldn't get any of them to really work. I know that solder mask can affect the the impedance by, you know, anywhere from 1 to 3 ohms. But the truth is we're talking about RF traces. You know, if you're trying to find the impedance of a certain trace, it's going to be most likely an RF trace. You can do high-speed digital traces as well. But most of the RF traces, you're going to, you know, I don't know if you can see this or not, but you're going to uncover them in mask anyway, because you don't want that capacitive interference and whatnot from the mask. So you're going to remove the mask anyway. So there's no point in putting it in there. I've tested them. I did a couple years ago, I used my VNA and, you know, put one port on either side of a board and measured the microstrip, and it was VNA, pretty accurate.
VNA, is it the small device?
Vector network analyzer.
Yeah. Do you have like specific product? Or?
I have an old HP.
Okay.
Yeah, and it has the Smith chart view. It's a vector network analyzer, so it has the Smith chart view. So I put it in Smith chart view and look at my S21, and I can see right where that impedance of that trace is. And it
so you manufactured some PCBs based on your calculator, and then you measured the tracks and you compared it with real measurement.
Yes, sir. Yeah.
Okay. I would like to mention, actually, many people, they sometimes forget that when they get numbers from PCB manufacturer, these numbers may be a little bit different because PCB manufacturer, they have to also consider the manufacturing process itself, which is going to change some of the parameters, for example, thickness of the electricum, and this could be like one of the reasons why the calculations in like this theoretical calculator may be a little bit different from what
That's
we
exactly
get from
that,
real
that's
PCB
exactly what the
manufacturer.
problem is. Even if even the EM simulators built into Cadence and Altium, yeah, I'm not going to say it doesn't matter, but you can spend a week simulating something just to make sure it's at 50.000 ohms, and you're going to manufacture, and you're going to be like, what's going on here? It's it's off. Well, because the manufacturing, it's not just manufacturing tolerances. One of the big things that happens, especially in FR4, you don't see it in the Rogers materials for the most part, but in FR4, if you have a multi-layer board, your dielectric constant can go down significantly after that pressing phase of the board. They can drop significantly, which will affect your impedance. I've also seen my first patch antenna I did on FR4. It was actually a 370 HR, and I called up Isola. I got the actual numbers for this exact part number that I was calling out. Here's the dissipation factor. Here's the dielectric constant at 1 gigahertz. My antenna was 915, so it was close enough. I modeled it, nailed it down in the model, built it, and it's way off. Well, why? Because it just is. I mean, I've seen from batch to batch of FR4 be off. I ordered one batch of antennas that were right on the money for the most part. Another batch was 10 megahertz off. So there are manufacturing tolerant differences that play in effect. I'm now using a Kappa 438 material, which I'm getting very consistent results out of.
Do you know why there is the difference?
In FR4 is just a glass weave. You put the pre-pregs together or the glue, and you melt them down, and things can change. Now the 2-layer boards, even though that they don't press and heat up, there's still changes. I mean, it's just FR4. It was
but
never
I mean,
really
do you know what is the difference between one material and the FR4 which you are using? Why the other material will not make so much difference?
Well, I mean, it's designed to be consistent.
Okay.
I'm not a chemical engineer for Rogers, but I know that it is designed specifically to be consistent from batch to batch, and from lower right corner of the panel to lower left corner of the panel to upper right corner of the panel, which also I would see in FR4. I would see variances on the same panel, just the way the glass weave, is pressed or heated up or just manufactured, from the factory.
Okay.
So but even the Kappa 438, I modeled that. I got the dissipation factor. I got the dielectric constant. I simulated it, and it was 15 to about 11 megahertz off. So I'm calling Rogers and saying, what is the exact dissipation factor at that frequency? And that's another thing that can happen is you look at the data sheets, and the decay might be measured at 1 gigahertz or 10 gigahertz. If you're running at 400 megahertz, those numbers might not be accurate for you. Or if you're running at 10 gigahertz and it was only measured at 1, those numbers might not be accurate for you at all. So you have to call them and get, sometimes there's a chart in the data sheet that will show you DK and DF over a frequency range for you to use.
Okay.
So, and that's where the differences come from. So back to the original, it's funny, you can simulate this all day long and think you're going to be great. You can spend $1 billion for an EM simulator, and when you manufacture it, it's off, and you're going to have to tweak it.
This is interesting point, actually.
Because unless you know exactly what the dielectric constant and the dissipation factor is after the boards have been manufactured, you're guessing.
Let's go to different tab. So which next one is the one which you use a lot? Or which was the biggest challenge?
The biggest challenge in this entire program is actually on this page here. It's the asymmetric strip line, which I have now put in the IPC 2141 model and the Brian C. Waddell model, because for whatever reason they're just different, and it's strange. I could show you. It would take a while, but I could show you an Excel file that I've done taking numbers from all three of I call it the default. It's not mine. It's a collage of different formulas that I find to be accurate. I think the narrow and wide came from Doug Brooks. I can't remember. It came from a publication from Doug Brooks, I believe. I'd have to look that up. It may have been Eric Bogatan. I don't remember. If I'm wrong, I apologize to either one or both of them. But it came from a publication. And so I've also modeled the IPC and the Waddell, and I find them to be off. Not off all the time. And this is the weird thing. This is why I put all three of them in there, because according to my chart, and I measured this against Sonnet, which I believe to be a gold standard. Sonnet is an EM simulator that I own, and I can measure.
Which one it is? Oh, can you search for name of the software?
Let's see. I actually have it. Yeah. This is it here. Sonnet. Yeah, Sonnet software. And Sonnet on the web.
What you can do here in this software?
This is a 3D simulator. What you can do is this is how I design my antennas. You draw in geometries. You draw in your layer stack up. It's complicated, but once you get to understand it, it's pretty simple. They make, if anybody cares, they make a free download version, Sonnet Suites. I believe there's a Sonnet.
There was a light version.
Yeah, there's a Sonnet Lite that I believe, is free.
Yeah, it says free and 2 stars.
Yeah. Yeah, it's free, and people can get to use it, and you can see that they can make a layer stack up. They can draw in their geometries. They can set up a simulation profile, and they can simulate it, and it will give you a return loss graph, and it also has a Smith chart plot if you need.
So this is also one of the softwares which you use to prove that your calculator values are okay. Okay,
yeah,
so we can go back to your calculator.
So the thing about the asymmetric strip line, why it's so challenging, is because all three of the formulas that I have included in here are the most accurate at certain geometries. It's very bizarre. The IPC 2141 might be the most accurate according to based against Sonnet at one geometry, but in others, I find that the default formula is accurate at most geometries. I have a chart. I desperately tried to find it this morning, but I can't find it, where I have an entire graph of geometries put into Sonnet, and I measure those graphs against these three formulas, and you can see at the 50 ohm spot, at any geometry right around 50 ohms, they all seem to converge, and they're all pretty accurate. And then at other points, the other formulas just start really rolling off. I don't know why. So I put them in there for people to use. The coplanar strip line, that is still a work in progress. I've gotten the formula from the Waddell book, I've spent hours and hours and hours on it. I can't get it to work properly. I don't know what I'm doing wrong, if I'm doing wrong, or if there's a typo in the book or something, because I can't seem to get it to model accurately.
This is good to know that it will be there, because some people, I have got some questions, people asking me how to calculate the impedance with with this kind of, or in this kind of situation when you have coplanar.
I do find I use this calculator myself on my products. I find it to be accurate according to what I've measured. The only problem is that I've got the formula that I use assumes a thickness of 2.1 mils. Again, the Waddell formula gives me the option to change that. I just can't get it to work. So I'm not sure where other people are getting their formulas, if they're using the Waddell, or if they know something that I don't. I don't claim to be a high-level mathematician. You know, I've taken all the calculus classes and differential equations and all of that stuff. So, you know, I do know some about math, and I've tried. I've made separate programs just to model that, and I just couldn't get it to work. So I've left that in there as what I consider to be a fairly accurate tool.
Okay.
And then the other one that I use a lot is which I think most people, I get the most questions off of the where is it, the differential pair calculator. And this is actually something that I just changed because a guy over in France had noticed that my my target Z diff was a little bit out of whack there. So I changed that this morning and made that. And the reason I put in here a tolerance for Z diff because most differential pairs, especially the older style 100 ohm ones, you can have a tolerance of plus minus 10%. They're going to work just fine. So, you know, if you measure your differential pair and you say, oh, geez, it's not exactly 100 ohms, you can see in here that, yeah, it's at 100. I measured 108 ohms. Well, that's still well within a 10% tolerance, and it'll work just fine. You can obviously change this.
Okay, how accurate is this calculation? Because this is also one of the calculators which I use most.
I find it to be pretty accurate.
So you measured this?
I've not done a differential pair measurement of it. If someone else has, let me know.
Okay.
But I have seen there was a guy over in Germany modeling differential pairs, and it was on some forum I saw, and he had actually referenced the toolkit, and the toolkit number was within reasonable accuracy. You know, again, these are combinational logic formulas. They're not going to be as accurate as EM simulators. And, you know, again, the same manufacturing tolerances apply to the differential calculator as it does to the impedance.
We were talking about this,
you can spend your day trying to get 100 ohm differential impedance, and you'll measure it, and it's not 100 ohms.
Okay.
But the truth is it's going to work. I've done a lot of differential pairs. I'll probably get dinged really hard for saying this, but I've never seen a product not work because the differential pair was a couple ohms out. I've just never seen it. Yeah, I did PCI 3.0, which is 8 gigabit, on a pretty high-end board we did a couple years ago. And they were very long differential pairs. I mean, I think they're like 8 inches or 10 inches long from end to end of the board. And I'm thinking, oh, you know, oh, great, this is going to look ugly because the customer required that I do post evaluation. So I had to rent this Tektronix oscilloscope, this $500,000 oscilloscope with differential probes. And I fired that thing up, and I'll tell you what, the eye diagram was crystal clear. So,
what was the oscilloscope? Do you remember what type it was? No?
It was a Tektronix something or other. I just don't remember the model number.
So you can rent it. How much was it? Do you remember?
I rented it for, I think $1,600 for the month. You know, you had asked me about if I could to go back to where was it? Conductor propers. You'd asked me about this, and I have to go here. If I set this down to 1, this is what I originally started up with. I got 127 ohms. Well, I made these boards. Here, and I've got, there's a bunch of different geometries, and the back side is actually a 600-inch trace, 5 mils thick. And I measure 125.7 ohms.
Nice.
And this is 127.45 based off the exact geometry that I'm using. So that's pretty accurate. And I talked to a customer a couple days ago who said, hey, I've used your toolkit and I just used it for a voltage drop. And he said it was right on the money. Well, for voltage drop of the trace to be right on the money, that means that not only the DC resistance has to be right on the money, but the conductor current had to be right on the money too. So that was actually a really good feedback. I asked him if he could share those results. He hasn't gotten back to me yet because it was just a few days ago, actually. So we'll see if he can come up with that. But that was really interesting because that shows me that a multitude of this page is working properly.
Okay, let's talk about Crosstalk calculator. This is interesting one because
sure.
I use this a lot in my videos, but recently I've done also some simulations. And basically, when you compare these theoretical values with the simulations, people ask why there is difference. Because in simulations or maybe on a real board, usually there is not so high coupled voltage as in this like super theoretical calculation. And in my opinion, it's because, for example, one of the reasons maybe there are like real drivers and these will have some real parameters or something. So what is your opinion about this theoretical crosstalk calculator?
Simulations are fantastic, but they're only as good as the model you put into them. It could be a variance in model. It could be some of the drivers compensate for some of this stuff. And I believe the formula in the toolkit is, again, a rudimentary formula that probably doesn't account for stray capacitance and fringe capacitance and inductance and other PCB parametrics and parasitics that your full-blown simulator will compensate for. I believe this is like a worst-case scenario type formula.
Yeah, I see it exactly the same way because these values, what you add into this calculation, there are only few values. You can't really describe PCB with
if you send me some of your results, I'd be happy to look into it and try to get you a better answer. But I believe that would be it. This is, again, a combinational logic style formula that's not going to have the ability to fully simulate all of the parasitics and whatnot.
Yeah, I agree. Okay. Click on something else. What other?
I'll point this out. I'll go through a few of them here. The VIA calculator is actually my very first thing. I get dinged on this a lot. How the VIA height changes the VIA current down here. That is according to the IPC 2152. So because so many people have said this doesn't make any sense, and I probably agree with them, I'm not saying the 2152 is right. I give people the choice of disabling that. Again, this is something from a spec that I've never fully vetted myself, so I don't know if the VIA height really affects current that much. It makes sense to me because there's more VIA wall for sinking heat, it makes sense to me. I don't know exactly how it is. I put that in there. If people don't like it, they can disable it. It's funny. I get a lot of feedback on that point.
So is the current higher or lower when height is higher?
So I'll show you here. You can see that if I enable it, the current goes a little higher. And did I have to keep it disabled? Yeah, disabled. So if I have 120 versus a 20, you know, it makes sense to me. It makes sense being that a small via doesn't have a lot of thermal mass surrounding it. So a smaller amount of current is going to increase the temperature of the trace versus a via with a lot of thermal mass around it. This is what they claim. I put it in there as
interesting. I never noticed this.
What about other people swear up and down that's wrong, so I say here, disable it.
But some of the other parameters, they are there only for capacitance and inductance, yeah? Like what, reference plane opening, diameter, that doesn't...
Correct, yeah. The via capacitance is a function of the distance, the gap in the reference plane to the via height, or I'm sorry, to the inner pad. If you don't have an inner pad, it's not going to work. This is, you know, again, this isn't. This is a more of a rudimentary type of calculation, assuming you've got an internal pad with an internal plane. The via inductance is fairly accurate. Modeling via inductance is actually pretty difficult to get it exactly accurate, but this one that I use seems to be pretty accurate, fairly accurate. There's things about step response in here. I have conductor cross section. Basically, I take the via and I lay it out, and I say this via laid out, split in half and laid out, is equivalent to a trace or a conductor of X width at X thickness, and the via plating thickness would be considered the thickness of the trace. And something that there's also now, you can do a 2-layer, and again, you can see that the impedance measurements go away. Micro via, again, I put a note in there. According to the IPC standard, micro vias react to temperature rise to current in the same manner as a through-hole via. That's them saying it. So I put that in there. Something new that a guy on LinkedIn, you might know, Bert Siminovich, if I'm pronouncing his last name correctly, has helped me out with is differential vias.
Wow, I didn't know you have this differential impedance. That's
that was new in, I think in 8.0, I put that in there. So there's all kinds, and you can do a full plane opening, and so yeah, it gives me all kinds of information. People are welcome to bombard Bert Siminovich. I might be pronouncing his last name wrong, so I apologize to Bert. He's out there on LinkedIn. He does a lot of posts, and he's sent me this, and he was a fantastic help for this. And then the minimum stub length here for if anybody if anybody cares about via stubs and back drilling, this gives you the some information on that. This is the minimum stub length of via to avoid unwanted resonant frequency nulls. So meaning at this via hole diameter, at this baud rate, we'll change it to 2, for example. You know, at 1 gigabaud rate, your via can be your via stub, which if you see the stub down here, can be 334 mils long.
Okay, I understand now.
Before it starts really affecting things. If you're up at 10 gigabaud, that goes down to 33. So if you've got an 062 board or an 090 board backplane, because some of these backplanes are thick. I mean, they're 90 mils, 125 mils thick. So that means if your stub length is longer than 33 mils, you're going to have to cut it out.
You need to do back drilling.
You have to back drill, yeah.
Gigabaud, is it like frequency is half of this, or?
Yes. Yes.
So 10 gigabaud will be like 5 gigahertz?
Yeah, I believe so. Again, this is something that Bert gave to me. I'll double check that, but I believe that's what it is. The anisotropy of the material, that's a bit complicated. You're going to have to look that up because it would take me a while to explain it. But 18% is sufficient for most applications. So you might not even need to worry about that.
The next step on the left of the VIA properties, on the left.
Oh,
Yeah.
thermal management. Oh, okay. Yeah, yeah. This is something I use this once in a while for heat sinks. Basically it tells you how good or bad your heat sink is. If your heat sink will be able to drop your part enough degrees C to handle it. Your part will be rated in a certain wattage. Like for example, even though that's an old style heat sink, if you look at FETs, an N-channel FET, it'll say it'll handle 120 amps. Well, that's great. That's 120 amps if you keep it at 25 degrees C. If the thing goes to 35 degrees C, it might only be able to handle 50 amps, and then up and up and up and up, and to the point where it's going to explode. So you can look at the power dissipation, say it's and the heat sink junction temperature will be this. So if your heat sink thermal resistance is 25 C per watt, which will be rated, if you look at the rating of the heat sink, they will tell you that. My device power dissipation, my device's power are dissipating 35 watts, so that claims that it'll be 898 degrees C. Seems a bit high. I have not played with this in quite a while. So a 2-watt power dissipation would be 73 degrees C, which sounds about right.
Mm-hmm.
And then the thermal junction resistance, that's, again, the same thing. The junction between the pad or the lead of the device to the board and how much heat can be dissipated that way.
Okay, I never really used this calculator.
Mm-hmm.
And
Yeah.
I'm thinking like, because in datasheet very often when you have, for example, regulators, they will tell
Mm-hmm.
you this junction and some other parameters, but you still need to like calculate the area, what you need for take out all this heat. And
Well, yeah, and this isn't going to tell you all of it. It's going to say if your thermal device or if your device thermal resistance from the data sheet is 3 degrees Celsius per watt, and the device happens to dissipate 5 watts, it means that junction temperature is going to be about
Mm-hmm.
38 degrees.
Mm-hmm.
Again, it doesn't compensate for different types of materials. I do a lot of LED design, and we put those on aluminum. I don't know how that affects things. This is, again, a rudimentary calculation for that.
Okay. Then the next one, PPM XTAL Calculator. I never use this one too.
Yeah, that's something that I've been considering making a toolkit specifically for engineering only. Not PCB design, but more of a double E thing, because there's a lot of things that I would also like to add, but I just don't want to clutter up the toolkit. I've got a lot of ideas in the future for things that I would like to make. This would be probably the first to go from the PCB toolkit into an EE. But bottom line is, I add things to the toolkit as I learn. Back in 2014, we designed an aircraft radio. It was reception only. It was just reception only, just to listen to pilots. It was more of a hobbyist kind of project that we're working on. Not our hobby, but the customer's project. He sold them. It was people that bought them was like enthusiasts. And we laid this thing out and it wouldn't work. And we spent, we spent 2 months trying to figure out why this thing wouldn't receive. And one day I decided to look at the crystal, one of the crystals that was driving the radio, the receiver chip. And I hooked it up to the spectrum analyzer, and I put my span down to like hertz, and noticed that the crystal was way off. And that was all it was. It was the crystal was driving the frequency way off into the IF frequency, way out of left field, and the IF filters was canceling it out. And what happened is the assembler put in like 130 ppm crystal versus the 10 ppm crystal I called out. So that gave me the idea of, it's like, I wonder what if we put in, if you put in your ppm value on your crystal, what does that really mean in plus and minus frequency? Now, the tab above that is actually pretty cool. I had just put that in version 8. This is the load capacitance values. These are general rule of thumbs. When you see a microprocessor, you'll see an 8 megahertz resonator or something like that, 8, 20, 50 megahertz crystal, and you'll see 2 capacitors hanging off of it. And this will give you those initial values of that. You open up the data sheet of the crystal, it'll give you a load capacitance value, possibly a straight capacitance value, because there's 2 ways of doing this, by the way. And this will generate my C1, C2 values. There's also a rule of thumb, which at the top of my head, I just don't remember what it is. I'd have to put a note in there, but it'll give you those values. Some
people ask me how to decide on the on these capacitor values when they are connecting crystal to a microcontroller, and yeah, usually you need to check the data sheet, or maybe there is application node or something, and they will yeah, there is some equation, I think, how you calculate it.
Well, this is it. This has a rule of thumb, which is, I just don't remember what the rule of thumb is. As far as picking that out, it has to do something with the load capacitance times 2 divided by something or something. I can write something up on this. I have to admit, the help file in the toolkit just goes out to a help page on my website, and it's really lacking. I really should put more time into explaining some of these things.
And so you can find more information about this somewhere on your website?
No, the help talk, I don't think.
Okay, you mean like you should improve the help. Okay.
Yeah, I don't believe it's incorporated into that yet, because it's fairly new. I haven't had a lot of time since version 8 came out to put in a lot of this stuff.
Okay, so if people don't understand something, they can always go here and maybe they can find more information.
Maybe, hopefully, but I'll admit there's not, not everything is in your PPM calc. Yeah, I have not put in that yet. I will promise I'll get to that and give people a little bit better explanation of what that means. But bottom line is, this will give you, if you look at your load capacitance in your data sheet, and it's typically, 8 ppf or 8 picofarad. And my straight capacitance is something, it'll tell you, basically what those are.
Rule of thumb.
So rule of thumb.
Yeah.
Rule of thumb. Yeah.
Okay.
Yeah. And obviously I've got an Ohm's law calculator.
I've seen this one, yeah.
Believe it, hey, I use this LED, again, LED bias. I use this all the time because I put LEDs all over my boards, and this will tell you exactly, how much current. Your typical LED, you want to run at 10 milliamps. They say 20 milliamps, but that's pretty bright for most. If you can use them, run them at 10, fine. And so if you've got a 12 volt, if you've got 12 volts going into it, you got typical LED is 2.1 volts actually. To run it at 10 milliamps, you'd need a 990 ohm resistor, and the wattage of the resistor is such. So that actually works out pretty well. I've got series resistors with the voltage drop. Here's the total resistance and the current and the voltage drop across each one. Same with parallel resistors. And I've added some RF RF calculators in here, a pi pad and a T pad, which are used, which is what we can get into with the antenna portion. These are attenuators. You can put these in series with your receiver. It happens a lot of times if your receiver signal is really high and you want to knock it down because it might burn up the input of your LNA or something like that, and I want to add 10 dB of attenuation to my receiver, here's the values in that configuration of resistors that I need to knock me down 10 decibels. Same with the T-pad. And it's something I just recently put in there for everybody. Capacitors in series, capacitors in parallel, inductors in series and inductors in parallel, and what those values are.
Nice.
Sure.
What about
What's
PDN
next?
Calculator?
PDN Calculator, I've redesigned that as well. I originally had it from a formula from a white paper that I just realized was just incorrect. It was either incorrect or it was missing something. Just something was wrong with it. So I redesigned it off of a better white paper where I don't know, I really don't know how many people use this, and I know Altium and other companies have high-end PDN calculators, but this is saying that my voltage rail is 5 volts. What's my maximum AC ripple that I want to see on it? My current through it is 2 amps. My transients, 50% of that means my PDN resistance needs to be 0.25 ohms or below. And if people are doing full planes on a board with a 1 ounce copper plane, you're going to be pretty close to that regardless. It's really for when, if you look at a core of an FPGA or something, and you've got a 1.8 volt and a 1.1 and a 3.3 or something like that, and unless you can afford to put every single core voltage on a separate layer, you're probably going to have to do split planes. So there might be a narrow portion of your plane that if you measure and you say it's, geez, this is like 0.6 ohms or something, you could have a problem. You could have a problem with ripple. Okay. And also I put in capacitive reactance and total plane capacitance, area of a plane, like 1 square inch of a plane, distance between planes, 2 mils, frequency. And this will tell me that 1 square inch of plane with 2 mil distance will be at 427 picofarad.
Okay.
If anybody wants, I can link to it. I probably should. I link to the in the toolkit. When I link to something, I link to something that I know is going to be around a while. A lot of times, if there's a PDF out there, I'll go back to it a year later and it's gone. Mm-hmm. So I don't like making links like that, and it's not my property, so I don't feel comfortable distributing someone else's PDF in the install. But if you look up power plane and power delivery network impedance, you will most likely find the white paper where this came from, and that will give you a lot more information on this.
Mm-hmm. Okay, what next do we have here? Planar inductors.
Minimum conductor spacing. This is based off the IPC 2221B.
Oh, actually, yeah, many people ask about this one because they would like to know what distance they should keep between tracks or something for different voltages. So we can talk about this one.
Yeah, this is, again, it's in the 2221B. I'm not an IPC salesman, but I'll tell you to go out there and purchase the spec. It's there for purchase, and it'll explain all of this. But it will give the values based on, is it a bare PCB? Oh, I've got them right here. Internal conductors uncoated at sea level. It's really for, I believe it's specifically for water vapor and water intrusion. It doesn't mean that there's going to be arcing per se, or that this is the UL, I don't remember what the spec is, 741 or something like that for the arcing, where you have creepage slots in a material. Sometimes you do creepage slots between high voltage or high potential pins, so dirt, dust, oil, and whatever doesn't accumulate on the board and cause a short. This is not what that's about. This is, I believe, in the 2221, which I don't have in front of me, is primarily for water vapor getting onto the board. And this will be, I use it. I use it as if it is a spacing. I do a lot of 125 volt, 125 volt work. And I've used this quite often for external conductors external conductors with a conformal coating of some type. External conductors uncoated, so the B3 I use, that's what it would be if it was uncoated. Uncoated means no solder mask. Internal conductors, I thought there was, yeah. And then here's if we go to the assembly, we can see the distance for coated or uncoated, or conformal coated and unconformal coated through-hole leads, for example. But it's a good rule of thumb to use. I use it. I use it quite often.
Okay. Next, mechanical. What's mechanical information?
That's something I haven't updated in quite a while. It's here's a 4-aught wire, for example. Or let's go to something more usable.
I always Google for these, and I didn't know it's in your calculator.
Yeah. Here's an American wire gauge standard of 30. Here's a 30 AWG circular wire, and the diameter is roughly 10 mils. Its resistance is 103 ohms per 1,000 feet. Its max amp for wiring, that's something you'd have to look up. The spec that I took this from they separated max amp for wiring and maximum amps for power transfer, meaning I think the maximum amp for wiring meant that's the maximum you want to put through that thing before the insulation starts burning up or something like that. And for maximum and maximum power transfer is what that's your rule of thumb not to exceed if you're using this for like a data cable or something like that.
Yeah, it says in the hint, I think.
Excuse me?
Yeah, for power transmission, yeah.
Yeah, 700 mils, 700 circular mils per amp rule. Yeah. There's, again, this is something that I put in a long time ago. I apologize. I'd have to look up exactly what they meant by max amp for wiring and power transfer. But I believe the because it says chassis wiring, I believe that's like the max you want to put through that thing before bad things start happening to that wire. But that's in here. Drill chart, basic drill chart.
Oh, we don't need to talk about this. Let's go to ER effective.
ER effective, where is that?
Second left from the mechanical information down, yeah.
Yeah, ER effective. ER effective is an RF term. It has to do with the geometry of the trace and the E and H fields creating what's called a cutting plane. And so you might think that, hey, my ER is 3.8. Well, but I'll just change that now, 3.8. But at this geometry and this frequency, my effective dielectric constant, what's used for many of the impedance calculations and whatnot, is actually 2.59. So it's not 3.8, it's 2.59. So if you look at the formulas, if you look in the back of the IPC books, you'll see a lot of times, or in the Waddell book, instead of calling out, what's the square root of ER, they're calling out what's the square root of ER effective. And that's where this comes in. So it's based off the geometry of the trace. And you can see that if I change this to like 5 gigahertz, you can see that it changes a little bit. But the real thing is the geometry of it, because of what's called the cutting plane of the EM fields. And I use this I send it to the wavelength calculator, because wavelength in the board, in the material, isn't the same as wavelength in air. Wavelength in air is going to be, your ER effective value is basically 1, where in your board material, it might be something completely different. So frequency of 500 megahertz, quarter wavelength is 3.6 inches. Where if I change this to 1, which would be air, it would be 5.9 inches. So that's where that comes from. So the ER effective changes, it changes your impedance, basically.
Okay, so we can go back to the wavelength calculator. So that's the next step. Again, very often I just go to online calculator and I find something. And actually, some time ago, I was doing a video and I used wrong wavelength calculator, the one which didn't consider the material. And
right, yeah.
And then I was wrong in the video, but I should know. I should use.
Yeah,
this.
in the RF world, you're going to see quarter wavelength all the time. Wilkinson bridges and things like that, quarter wavelength. To make a circular polarized patch antenna, you have feed number 1 going in, feed number 2 being a quarter wavelength difference. And you need to know your ER effective to get that quarter wavelength, or you'll be way off. So that's where that comes from. And I put some information in here about wavelength information, ER effective information from, I believe this is Microwaves 101, has a really good discussion on what K effective is. And I also put in speed of light, because speed of light, the real speed of light is like 299 something kilometers per second, versus the 300,000 that everybody uses. I don't know why I put that in there. I just figured I'd put that in there. So that's where that's from. And I even have the formula, lambda over C divided by frequency times square root of ER effective.
Okay, go next step.
Oh, and I should put on, you can also do the period.
Okay.
Period in nanoseconds. If you want to equate a 1 nanosecond period to some frequency, here it is. If you want to deal in nanoseconds versus the straight frequency. What you got next for me?
Well, you can click on this one. Yeah.
XL?
Yeah.
Pretty basic. XL, XCXL based on frequency. And it's down here. The values are down here at 1 megahertz. At 1 megahertz, the capacitor and inductor is going to have an XL of 0.15 and an XL of 6283 ohms. A lot of times we use blocking capacitors in RF to differentiate between sections. And for example, I've got one working right now where they put in 100 picofarad capacitors, and the frequency is only like 250 megahertz. Well, the X of C is 6.3. So you're losing a lot through this capacitor. We changed those to 0.1 microfarads, and you can see that I'm way down now. So the capacitor isn't affecting the RF transmission as much. It's simply there to block DC between one stage and the next, and not to interfere with the RF signal itself. So the 100 pico
because also the resonant frequency is very low. That's the reason.
Yes, correct. Yeah, if I go back here, it's 6.3. If I change this to we'll say 2450 meg or 2500 megahertz, obviously it's going to lower. Now keep in mind these are ideal components. In the real world, the X of C of a capacitor actually goes down, and then it starts going back up because of what's called mutual inductance. There, the capacitor has inductance, so the resonant frequency is going to force it to go back up.
Okay. What is next? Planar inductors?
That's something I put in a long time ago. I don't think anybody uses them anymore. Yeah, honestly, I'll be honest with you, because unfortunately they're not very accurate.
I have never used this.
Planar inductors only seem to work at the chip level. I've talked to some of these guys that are doing it. They say they just don't work on boards in large areas, but on the infinitesimally small area of a chip, they work fine. So I don't know if anybody uses it. You're more than welcome to tell me if you have. I've never personally used it. I put it in there as a request, I believe. I don't remember exactly. Again, this is something I put in there a long time ago. But I've never used it.
Okay, what next? What else we have not been talking about?
Embedded resistors. This is gives you the resistance based on resistor size, length, and the area itself. And there's a couple different types in there. There's additive screen process, subtractive copper nickel, embedded annular resistor. So yeah, someone over in Japan had sent me this a long time ago and wanted me to add it in there, and sent me a PDF, because a lot of these things do come from people that just want me to add things in there, and if I think that it's a valuable tool set, I'll put it in. It's not necessarily that it's something that I personally have used or am intimately familiar with. Sometimes people like the Via stub thing from Bert. Here, this is something really cool you could put in there. Will do. If it's something useful and someone's got the formula and can verify it, I'll take a look at it and put it in possibly.
Maybe now you will receive some other some
possibly.
other tips. Okay. Yeah. Bandwidth and max conductor something length. The first one, very first one.
Yeah. This one is a little complicated. You do want to look at the 2251. What this is saying is maximum conductor length, maximum length the conductor can be before it is considered a transmission line. Bottom line is that not everything has to be a transmission line. If the frequency is low, like for example, 250 megahertz, the bandwidth is so long that it doesn't even matter what my impedance was. If it's 50 ohms, great. If it's 58 ohms, whatever, it's not really gonna matter. My traces are short. The bandwidth and the wavelength is so long that it just doesn't matter. And so if you can do this, for example, a 100 megahertz signal, the full wavelength in air. This is how the frequency domain method that is called out in the IPC manual says. What they say is they take the full wavelength of air, in air, and they divide it by 7. And this is it. It's so your trace could be 16.8 inches long before it's considered a transmission line.
So this is basically
the bottom line is you don't have to worry about it.
Yeah, that's what I wanted to say. So that's the length when you need to start worrying about
Yeah, we go up to 2,500 megahertz, and guess what? That drops down to 0.67. So if your trace is longer
Can we
than...
change it to metric so also people, like from Europe?
Sure.
Okay, nice.
There you go. So your trace can be 1.7 centimeters long. And I put this in here because some people like to go out to 1/20th. I've heard some of the engineers like to use 1/20th, but however you want to use it. And then the signal, you can also base off signal rise time that
So
converts.
this would be, for example, the time between 10% up to 90% of rising on or falling edge.
Correct. And that's in the 2251. I do remember this specifically, where there's a formula to convert rise time to bandwidth. And I use the propagation speed and maximum conductor width. And they use a SR divide by factor in the 2251 that if you've got, you can look it up. But bottom line is, this is telling me, what it's telling me is how long does my trace, at what point in length do I have to consider my trace a transmission line?
This is interesting. Again, something I didn't know it's in your calculator, and I searched on internet. I have to remember all these calculators, or next time I have to first open Saturn PCB and have a look if maybe the calculator is there, and then start searching on internet. Yeah,
it's there's sometimes I forget that it's in there, and so yeah, I can go to the toolkit. And like there's a lot of information in Padstack calculators. Through-hole Pad spoke with, in all honesty, this is just a guideline. You don't have to follow this. It's just a guideline. BGA Landside, this is something that does come from the IPC, the nominal ball diameter.
I didn't know you have this. I always search for application nodes, and
I should start advertising more. But yeah, this is so you can get the nominal ball diameter from the data sheet, and you can create your footprint accordingly. And you see the IPC uses the larger land variation, so you would actually use 0.6 millimeters as your pad in your footprint. And the same thing with conductor, how many traces can I fit through this?
People keep asking me, like, how did you come up with the size of the path around through hole? And I always say, like, I printed it and had a look, and can I solder it? No, then make it wider.
Yeah, that's what this is for. So this will give you, you can play around with the values to see what kind of trace you can get through conductor pins. The same thing on a surface mount basis. And then something new I've added is a differential pair. So this will tell you if you can or cannot get your differential pair, or what you have to tweak your pads to in order to get a differential pair through there. Same thing, obviously, with the surface mount. And then there's a corner to corner, which is a Pythagorean theorem, A squared B squared thing, because a lot of pins are square. So how do you determine what the hole size should be on a square pin? Well, you're looking Pythagorean theorem, and this will tell you and suggest a drill.
Nice. Did we go through everything?
PDN planars, thermal management via wavelength, XTAL, embedded, yes. I got to get back to you on the PTF. effective, mechanical, minimum Ohm's law, Padstack, yes. Conductor impedance, properties, conversion. I have conversion calculator. Obviously, this is pretty self-explanatory. And I've also got down here some links. One of my favorites is this capacitor chart from Just Radios. Now, a lot of people will call out capacitors in nanofarad values and like, well, what is that? This will tell you. It's a good chart. And same thing with a DBM chart. There's a DBM chart and Ohm's law and
what is
SI.
DBM? chart.
This will tell you,
Oh, I've seen this one.
yeah, for example, I'm building right now, I'm building a, where is it? I'm building right now a 2-watt transmitter for a customer. So at 2 watts means my peak voltage is 10 and my dBm is 33. So if somebody says, hey, I need a 33 dBm transmitter, you know it's 2 watts. You should probably have memorized that by now if you're an RF engineer, but if you don't know, here's a fancy chart to tell you. And it also gives you obviously the peak voltage value.
So all these tables are in your calculator?
There's a link here to a page that I know will be around.
Yeah, I see. Yeah, I see.
And this one comes from Mini Circuits. So I linked to, and it opens up at Shell executes your browser and opens up that PDF.
And the calculators, what you have there is what? Or unit conversions, distance conversion.
Yeah,
I always use Google for this, by the way.
For what now?
Google. I always like 10 mils to millimeters.
Yeah, I could make this. Better. There's better tools out there for doing this that have all of the values, and you don't have to switch between metric and whatnot. But this was the best I could come up with, and unless I wanted to make an entire tab for just distance conversion, which I really.
dB rectangular to polar angular. Okay. And that's the last one, I think. We went through everything.
I believe that is the last one. Yes.
And
obviously I've got options down here. Etch factor. If you want to play around with etch factor of the trace, aspect ratio for your vias. The aspect to of a via is it's a ratio between the diameter of the drill and the length of the via. You try to want to maximize at 10. So that's a setting in there that's I believe
where is it used?
In the via properties. There's an aspect ratio. So at this hole diameter with this via height,
it calculates. Okay.
I'm at a 6.2, so I'm pretty good. If I go below that, it'll turn red. Unfortunately, if you turn the toolkit back to I like the dark theme the best, but if you just go back to the regular Windows theme, then everything seems to work better. For example, if I change this to 150, you'll see it turns red. For whatever reason, the theme won't change colors. Once I go into the dark mode themes, the reds, my warning labels tend to go away. I don't know why that is. I hope maybe they fix that in the future, because it's not like I'm calling out anything different. Same with the conductor properties. You can see my skin depth changes. I don't remember what it was. I'm sorry, 1 megahertz. See, and the skin depth percentage it's a ratio of 1/2 the thickness of the trace itself. Again, it's out there for people to Google search, but the percentage is my depth is greater than the thickness of the trace, so we're okay. If I start bumping the frequency up 50, go to, now I'm at 70, 78.26, which is my skin depth is 0.27, my thickness is 0.7, so I'm below that 1/2 mark. Again, that's all out there for people to look at. But obviously the IPCs, copper weight, you can enter copper weight manually because some people, I'm old school. To me, copper will always be 1.4 or 0.7. I know that it's 0.635 and 1.35. Some people are sticklers about that, so you're welcome to enter that manually if you like. Or other times there's custom boards plated. I've seen boards that were plated 33 mils or 33 ounces. I mean, they're literally like this thick. So
I didn't know you have this option, actually. Again, something new, what I learned today.
I have to change my my advertising skills. But that's okay. That's okay.
Okay. Actually, I think we can make one video from this.
Okay.
And I know you also do some work with antennas. So maybe what we can do, we can just mention something about antennas, and if people if they would like to make us a video about antennas, then we can do it. So what we could talk about antennas, what you could maybe share with others if we would make this video?
I've got an entire list of start to finish on basic antenna theory.
And that's it. That's everything for today's video. If you would like to see another video with Ken, where we would be talking about how to design PCB antennas, leave comments. I would like to thank you very much to Ken for finding time to create this video. Thank you, Ken. And I would like to thank you for watching this video and leaving your comments. Let me know what kind of calculator you use, or for example, what is your experience, how accurate these calculators are, or if you are using Saturn PCB or if you are using something else. Because this kind of calculators are super useful, and every hardware design engineer uses some kind of calculator to do the schematic, or especially during PCB layout. That's it. I would like to thank you very much for watching. If you would like to see my next videos, don't forget to subscribe, and see you next time. Bye.